We learned that in order for a semiconductor material to be useful, it needs to be doped with an impurity atom, and it could be a piece of semiconductor material into an intrinsic semiconductor material, usually silicon, so that part of it is p-type and the other part is n-type, where it carries our free electrons at the junction. This makes the n region lose free electrons and creates a layer of positive charges near the junction. As the free electrons combine with the holes in the p region also loses holes and creates a layer of negative charges near the junction region. In reality, the depletion region is formed in an incredibly short amount of time, and its width is very thin compared to the p and n regions. The depletion region will continue to expand until the total negative charge in the depletion region repels any further diffusion of electrons into the p region. This time, the depletion region will continue to expand until the total negative charge in the depletion region repels any further diffusion of electrons into the p region. This time, the depletion region acts as a barrier to the movement of electrons across the junction. In the depletion region, there are many positive and negative charges on opposite sides, and as described by Coulomb's law, if there's a positive charge and a negative charge near each other, there is a force acting on these charges. In order for the electrons to move through this electric field, a certain amount of voltage equal to the formation of the p-n junction and the depletion region through an energy diagram. The energy levels of the valence and conduction bands in an n-type material are lower than the valence and conduction bands in a p-type material. This is because trivalent impurities exert lower forces. Energy diagram for a p-n junction at the instant of formation, we can see that the valence and conduction bands in the n region are at a noticeably lower end of the conduction band in the p region over electrons in the lower part of the p region conduction band. Temporary because, after crossing the p-n junction, these free electrons rapidly lose energy and fall into the holes in the valence band of the p region. As the free electrons from the upper part of the n region conduction band cross the junction, the depletion region starts to form and expand, but the energy level of the n region conduction band also starts to decrease. This process will continue until there will be no electrons left in the n region conduction band with enough energy to cross the junction. At that time, the junction is at equilibrium and the depletion region is
understand diode current, the interface. Equilibrium levels of carriers can be calculated very easily. In the N neutral zone, we know that N, the concentration of holes, is equal. This happens when we assume full ionization. Using the mass action law, we can also find the level of holes on the N side of electron side, and this is the level of electrons on the. Let's take a look at it. Appears. It's very important to understand that a Fermi level can only be electron bias p-n junction. We cannot properly call this a Fermi level. So what is a quasi-Fermi level? It is a Fermi level, or it's an energy level that exists in a region that is not at thermal equilibrium. Particularly important for the way for each of them, Fermi of V, a single Fermi level is used.
Hello.
In this video, we will discuss current components inside a PN junction diode, and we will also derive the diode current equation. In my point of view, more than the derivation itself, the assumptions that we make while deriving are more important to understand. Depletion exposed donor ions on N side is positive, and exposed acceptor ions on P, we have drift current negative. The exposed donor ions take a few is current components inside a PN junction diode, and we will also derive the to understand. Depletion width is W, and the electric field is directed from N side to P side because the exposed donor ions on N side is positive and exposed acceptor ions on P side is negative. As a result, electric field is directed from positive charge to negative charge. And because electric field is there, we have drift current, drift, and at the same time there is diffusion as well in the opposite direction. Under equilibrium, these two components would balance out each other exactly. As a result, you wouldn't see a net current flowing through the PN junction as we didn't apply any potential difference. We assumed P side doping is higher than N side. That's why the depletion width on P side is smaller compared to the depletion width on N side. Let me electric field inside this in this direction. And now let us apply a potential difference across this PN junction. Let's say the potential difference we are applying is V. And let me also assume that the potential we are applying is directly getting applied across the junction, which means I'm neglecting the potential drops across the neutral P region and neutral N region. And the electric field because of this potential would be in the opposite direction. As a result, the net electric field would be in the same direction as that of the equilibrium case, but the magnitude of electric field would have reduced, because of which the depletion width would also decrease. Let me reflect that on this figure. Because the electric field at the depletion region has decreased, the drift current would reduce as well, because the drift current at the junction is caused by the electric field. As electric field decreased, the drift current near the junction would decrease. In equilibrium case, the electric field was holding the diffusion current that we would see would be, as we said, there would be diffusion current. Now holes would be getting diffused through the minority carrier concentration. Now, because of the excess carriers came into the n-site, there would be a concentration gradient. As a result, the excess holes would diffuse through the n-type material. While doing so, they would recombine with the majority carriers' electrons. And as a result, as they move forward into the n region, the concentration of excess carriers would decrease. And if the n-type material length is long enough, then the excess carrier concentration of holes would reduce to 0 before they reach the end of the n-type material. If you keep this potential constant, then holes would be injected across the junction onto n-site constantly, which means the hole concentration on neutral region should decrease. But charge neutrality reasons it cannot decrease. As a result, the holes should be supplied from outside. But as this contact would be metal, there won't be concept of hole in metals. As a result, holes can be introduced if the supply takes the electrons. So that the hole concentration here wouldn't reduce, and the number of electrons the supply takes out would be equal to the number of holes injected across the junction. As these holes are different concept of holes injected across the junction onto n, before they reach the majority. As a result, the excess holes into the let me take the equilibrium current. Now holes would be getting diffused through the depletion rate concentration. Now, because of the excess carriers came into the n-site, there would be a concentration gradient. As a result, the excess holes would diffuse through the n-type material. While doing so, they would recombine with the majority carriers' electrons. And as a result, as they move forward into the n region, the concentration of excess carriers would decrease. And if the n-type material length is long enough, then the excess carrier concentration of holes would reduce to 0 before they reach the end of the n-type material. If you keep this, then holes would be injected across the junction onto n-site constantly, which means the hole concentration, charge neutrality reasons it cannot decrease. As a result, the holes should be supplied from outside. But as this contact would be metals, there won't be concept of hole in metals. As a result, holes can be introduced if the supply takes the electrons. So that the hole concentration here wouldn't reduce, and the number of electrons the supply takes out would be equal to the number of holes injected across the junction. As these holes are diffusing in the n-type region, they're combining with the electrons, so the number of electrons should reduce. Again, charge neutrality reasons, the electrons cannot reduce in n-type material, which means these electrons would be supplied by the source. The electrons injected across the junction, it cannot decrease. They diffuse and recombine with the holes. And again, this hole concentration cannot decrease as a result with the injected electrons. And if you see that the number of electrons supplied into the p-n junction diode by the source would be exactly equal to the number of electrons taken out of the diode by the source. We call this number of electrons flowing per unit time as the current flowing through the diode, I. But as this injection process, diffusion, and recombination process happens constantly, the concentration in the n-type material should not be changing with respect to time. But we don't know exactly how the distribution is with respect to distance. In order to find that, let us go back to the over del T, the minority carriers holes in n-type. The whole concentration on n-side wouldn't be changing with respect to time. So this should be 0. And we can write the continuity equation for this as Gp minus Rp. And we can rewrite this as del square Pn over del x square can be written as Rp minus Gp over dP. And we know Rp minus Gp is the net recombination rate U, which we have seen is given by hole concentration minus the thermal equilibrium hole concentration divided by the lifetime of holes tau p. And we have dP here. Now we can rewrite this expression as del square of, in place of Pn, writing Pn minus Pn naught wouldn't change anything. So let me take Pn minus Pn naught over minus Pn naught over dP tau p. And we can write the solution for this differential equation as Pn minus Pn naught is equal to C times e power minus of x by Lp. We can represent minority carrier concentration with respect to distance. And thermal equilibrium concentration is Pn naught. Let's say this is thermal equilibrium concentration, Pn naught. And because of the injection, the carriers would be high at this point. And as they diffuse, they recombine. That's why this graph looks this way. This graph would be for Pn of x. But what is the concentration of Pn at xn? That is the question. If you know that, then we can potential across the junction is given by Pn naught is equal to P naught is the question. If you know that, then we can find of x. But what is the concentration of Pn at xn? That is the question. If you know that, then we can find what is C. If you go back and see thermal equilibrium p-n junction, where the carrier concentration relation with respect to the potential across the junction is given by Pn naught is equal to P naught times e power minus Vbi over Vt. This equation, we call it as junction law, as it is relating carrier concentrations at the edge of the depletion region with the potential across the depletion region. But now, as we apply the potential would be, as we apply the potential V, then the potential across the depletion region would be Vbi minus V. So over Vt exponential, then concentration on n-side would be given by this. But these concentrations are not under equilibrium. This is under the applied potential. But the problem with this is we don't know either of these quantities. Then we need to make some assumption If we assume the injected hole concentration is far less compared to the electron concentration in the n-side, and similarly the injected hole concentration is far less compared to the electron concentration in the n-side, and similarly the injected electrons onto the p side is far less compared to the hole concentration. Under this assumption, we can say the majority carrier concentration is very close to the majority carrier the injected electrode hole concentration. To make some assumption, then we need to make some assumption. If you assume the injected hole concentration is far less compared to the electron concentration in the n side, and similarly the injected hole concentration is far less compared to the electron concentration in the n side. If you assume the then we need to make some assumption If you assume the injected hole concentration is far less compared to the electron concentration in the n side, and similarly the injected electrons onto the p side is far less compared to the hole concentration. Under this assumption, we can say the majority carrier concentration is very close to the majority carrier concentration under equilibrium itself. So we can write this expression as concentration is very close to the majority carrier concentration under equilibrium itself. Similarly, the injected electrons onto the p side is far less compared to the hole concentration. Under this assumption, we can say the majority carrier concentration is very close to the majority carrier concentration under equilibrium itself. So we can write this expression as Pn is equal to Pp naught times e power Vbi minus V over Vt. Our interest would be finding this quantity, which is Pn minus Pn naught. Pn minus Pn naught can be written as this equation, where we can take Pp naught times e power minus of Vbi over Vt as common, and we can write this as V over Vt minus 1. And we know this quantity is nothing but Pn naught. So we can write a Pn minus Pn naught as Pn naught times e power V over Vt minus 1. Now, as we know this quantity, now let us find the constant C in this equation. We know that Pn minus Pn naught at x is equal to xn should be equal to this quantity, Pn naught times of xn over Lp times e power xn over Lp. So substituting back, we get the expression for P as xn over is equal to np naught plus np naught times on minus xn over Lp. In similar lines, if we try the np naught xp over ln thing in negative x direction. So let me plot that values here, x minus, then x. And the reason for showing Pn naught is greater than np naught is because the p side is highly doped, so minority carriers will be far less compared to n side minority carriers, as n side doping is less. And because the doping on p side is high, this delta that we see would be higher compared to this delta. We have found the carrier concentration variation with respect to space of minority carriers. Now let us find, because of this carrier concentration gradient, we have diffusion current. Diffusion current density of holes, Jp diffusion, is given by minus q dp del p by del x. We can find this value, which would be equal to minus q times dp by vt. We can find this value, which would be equal to minus q times dp Pn naught times e power v by vt 1 times e power minus of x minus xn over Lp times minus 1 over Lp. So we can write this as, similarly, we can find Jn diffusion, which is given by q dn del n by del x, where this n is minority carrier concentration on p side, which we know here. So we can find the expression for this, which would be, now let us plot how this diffusion currents are varying with respect to distance, because from this equation it shows that they're actually changing with respect to distance. To make space, let me remove the unwanted stuff here and just keep the needed ones. It will be convenient to talk about currents than current densities. So I'm writing current IP diffusion in terms of current density, Jp diffusion. Jp diffusion units is amperes per unit area, so diffusion to the A, and Jn diffusion into ion diffusion by multiplying this with A. We can see that the diffusion currents are actually changing with respect to x. So let us plot these functions with respect to distance. I'm taking current on y-axis, distance on x-axis, representing the edge of the depletion region on n side with xn, and edge of the depletion width on p side as minus xp. Now first try IP diffusion at x equals to xn, the value would be just this quantity, as exponential would be 1. So let's say the value is somewhere here. And as x increases, and similarly, as exponential value would be 1. And as np naught is less compared to pn naught, because p side is highly doped compared to n side, the magnitude of ion diffusion at x equal to minus xp would be smaller. Diffusion current of electrons decreases as we go deep into the p side. So this is ion diffusion. But when we apply a constant potential, the current through the p-n junction should be constant. Whereas we are seeing here that current is actually changing with respect to distance. But then we are missing some point. Let's take this electrons as example. These electrons are diffusing because electrons were actually injected from this side.
So in the last few videos, we've been talking about the theory for PN junctions and PN junction diodes. In this video, we're going to do a PN junction diode example. And I'm going to show you just how I work through these kind of problems and why I think they're important to do. So the primary reason examples are important to do is to actually get comfortable with the math. So we want to get comfortable with the units in particular, and with doing quick unit checks when it's feasible to do so. And generally it will be, because enough stuff is going to cancel out that'll be fairly straightforward to do. And we also just want to get comfortable plugging stuff into a calculator. So we want to get comfortable with our calculator. I have a TI Inspire, fantastic calculator. So for reverse PN junction, which is the WN, we're going to try and find the reverse saturation current density JSAT. So how do we do this? Well, we know that JSAT is just equal to two components, JNSAT plus JPSAT. And we always want to start out with the simplest possible formulas, and then we'll break them down piece by piece, and then we'll sort of work backwards to actually find ourselves an answer. And we'll be checking at each point to see if the answer seems reasonable. So we know that the reverse saturation current density for electrons is just Q times dN times NP naught, where NP naught is the electron concentration on the p side at equilibrium, all divided by Ln.
Hello everyone, welcome to my channel Learning Electronics. Today we are going to learn reverse saturation current. So please subscribe my channel and also press the bell icon for more updates. Junction diode, when diode is in reverse bias condition, is called